Okay. So, we have just seen this one that Z per unit is equal to magnitude of V per unit square upon S conjugate load, that per unit, right. This is equation 15. So, the impedance of generators, transformer and motors supplied by the manufacturer are generally given per unit values on their own rating. That means, when you are buying a generator or transformers, right, or motor, you will see that on the nameplate that MVA rating is available and per unit reactance also it is available, right. In general, per unit impedance, right. So, for power system, all this must be expressed in per unit values, just because of your easy calculation. That only thing is that you have to transform everything on a common base, right. So, when base quantities are changed from MVA old to MVA base new and from KVB old to KVB new, the new per unit impedance can be given as it is something like this, that suppose this formula I have written, just now I will show you that this is frequent, this will be this is equation 16 and this will be frequently used, that Z per unit new is equal to Z per unit old into KV square base, that is old, right, divided by MVA base old into MVA base new divided by KV base new square. This is equation 16. That means, for example, suppose you have per unit impedance or reactance or resistance whatsoever. Suppose you have, this is your Z per unit old, right, this is the old value, and this value on its base we are writing, that is KV base old and MVA base your new, right. Therefore, this Z base old is equal to your KV base square, right, old divided by MVA base old, right. So, this is the base impedance for the old base. Therefore, you convert this Z per unit old into ohmic values. That means, your Z ohmic values, right, I can put this one is equal to Z per unit old, this is per unit values into Z base old, right. So, this is actually ohm, right, because this is your Z base old. So, multiply, that means, it is multiplied by Z pu old into KV square, right, just hold on, KV square base old divided by MVA base old, right. So, this is the ohmic value. Now, suppose new base value is given, say that is your, suppose this is given, you have to transform with for this one. Suppose this is your KV base new and say MVA base new, right. Therefore, Z base impedance, that new value is equal to KV square B new divided by MVA base new, right. That means, this is the new value, this is actually ohm, this is the new value. Therefore, therefore, your Z new, right, I can write that Z per unit values new is equal to your Z, that ohmic value whatever you have got here, this ohmic value, this ohm divided by ZB new, right. Now, this Z ohmic value is this one, you substitute here, and this J and this ZB new is here, KV square base new by MVS base, you substitute here, then you will get this expression, that ZPU new is equal to ZPU old KV square base old upon MVA base old into MVA base new upon KV square B new, right. This is equation 16. Actually, no need to remember anything, no need to put it in your memory, just old impedance you convert and that corresponding base is given for that. So, for which you can compute this part, right, and divided by your the new base impedance, right. Now, next is that this is equation 16. For numericals, this has to be used frequently, right. So, per unit representation of transformer. So, we have seen that a 3-phase transformer can be represented by a single phase transformer, because it is balanced, it is a balanced system. So, it can be represented for obtaining per phase solution of the system. Now, just hold on. So, now this is the single phase diagram, right, representation of a this thing. Magnetizing impedance is neglected for this one, for the timing, no magnetizing impedance is considered, right. So, this side we refer to as a primary, this is figure 8, right. It shows a single phase transformer in terms of primary and secondary leakage reactances ZP, this is ZP primary side and this is ZS, right. And this is your terminal voltage Vp and this is your secondary side is Vs, right. And voltage Ep is across the winding and Es primary winding and Es is across the secondary winding, right. And turns ratio it is given as 1:A, right. 1:A means just I will tell you very simple thing, you know it, right. 1:A means that is, suppose primary side turns ratio is N1 and secondary side turns ratio is N2. So, N1 is to N2, that means it can be written as 1:N2 by N1 is equal to 1:A, right, and A is equal to N2 upon N1. So, N1 is the primary side turns number of turns, N2 is the secondary side number of turns. So, A is equal to N2 upon N1, right. So, that is why transformation ratio is given 1:A, this way we will do, right. Now, this whole this thing you have to write down the your equivalent your voltage equations refer to primary or secondary. We will see that both are same in per units, right. So, let us choose a voltage base on the primary side. Primary side voltage base we are choosing VPB, P stands for primary and B stands for base, right. And on the secondary side we are making it VSB, A stands for secondary and B base. So, VSB. Also we have to choose a common volt ampere base. So, that is your VA base, right, it is volt ampere base for this transformer, right. Now, and this is the your what you call this one, that means V primary base upon VSB base, it can be written as 1/A. It is as you know that if it is primary side voltage is Vp, secondary side voltage is Vs, right, then your I am making it here. If primary side voltage is Vp, secondary side voltage is Vs, so Vp upon Vs, right. So, is equal to, you can write that primary side winding is a number of your turns N1 and this you know the secondary turns N2, right. This one also can be written as VPB base upon VSP base, right. That is why we are writing. So, that and your A is equal to we have seen that A is equal to N2 upon N1, that is why this one actually 1/A, right, because it is N1 upon N2, but A is equal to N2 upon N1. So, that means VPP upon VSB is equal to 1/A, right. Therefore, as the volt ampere base is common, we can also write IPB by ISB is equal to A. You know, if the primary is, hold on, if the primary side current is IP and secondary side current is IS, that you know it is N2 upon N1, right, and N2 upon N1 just we have seen that is equal to actually A. Therefore, this one also can be written as primary side base current by secondary side base current is equal to A, right. So, that means we are writing same thing, that primary side base current by secondary side base current is equal to A. This is actually equation 18. Therefore, primary side base impedance ZPB is equal to primary side base voltage by primary side base current. This is your 19. Similarly, for the secondary side, the base impedance VSB upon ISB, that is secondary side base voltage upon secondary side current, base current, that is equal to equation is equal, this you can be say 20, right. Therefore, from figure 8, right, your secondary side voltage from figure 8, you can write, you apply your Kirchhoff's second law in this loop, right. So, it will be Is into Zs plus Vs minus Es is equal to 0, right. That means this Vs is equal to actually Es minus Zs into Is, this is equation 21, right. This equation we are writing from this figure 8 and on the secondary side, apply KVL, right. Therefore, and similarly EP is equal to, here EP is equal to IP into Zp plus EP minus Vp is equal to 0. Therefore, EP is equal to Vp minus Zp into Ip, this is equation 22. So, secondary side and primary side, these two voltage equations are written, right. So, once this is actually one thing you should see, that here we are writing the terminal voltage, right, and this is second time primary side we are writing this voltage across this winding EP we are writing, right. Also, this Es upon EP is equal to A, that means it is something like this, that this voltage is EP, this voltage is Es, right. So, what we can do is that your this thing, that EP is the primary voltage and Es is the secondary voltage, that is equal to N1 upon N2, that primary number of turns N1, secondary number of turns N2, right. That means this one actually is equal to 1 upon A, that means your Es is equal to A into EP, right. So, this way you can this thing what you call this this equation Es is equal to A into EP we are writing here, just now I showed that Es is equal to A into EP, right. So, just one thing here, actually it should have been EP upon Es, right, this correction, right. Actually I did not look at the figure, it is EP upon Es, right. So, that is equal to VPB upon Vs, it is not Vp upon Vs, it should be EP upon Es, right, because I did not look at the figure at that time, right. So, it is just EP upon Es instead of Vp upon Vs, right. So, this one your, therefore, this Es is equal to AP, you substitute Es from equation 23, I mean this one into equation 21, here you substitute, right. If you do so, you will get Vs is equal to A into EP minus Zs into Is, right, that is equation 24. So, now substituting EP from equation 22, that means from this equation 22, this EP you substitute here, right, in that is into equation 24. Then what you will get, this one, that Vs is equal to A into Vp minus Zp Ip minus Zs Is, this is equation 25. Now, this equation we have to convert it to per unit form, right. So, what one can do is that when you are trying to convert it to per unit form, then simple thing is that Vs is equal to, this is a real voltage, is equal to say VSP, Vs per unit voltage of the secondary side into VSB. This is actually into this Vs is equal to, look, this Vs upon VSB is equal to Vs, this is per unit voltage, that means Vs is equal to, you can write Vs per unit into VSB, right. That is why instead of Vs, we are writing a VSP into VSB is equal to A. Similar way, that Vp, this Vp you are writing on the primary side base voltage is Vpb. So, Vp upon VPB is equal to your VP per unit, right. That means VP is equal to VP per unit into VPB, right. That is why here we are writing VP is equal to VP per unit into VPB. VP per unit means these are per unit values into primary side base voltage, right. Similarly, ZP, that same thing, that ZP upon ZPB is equal to ZP per unit, right. That means ZP is equal to ZP per unit into ZPB. So, this ZP actually replaced by ZPU and ZPB, right. This is the per unit impedance. Similarly, IP case also, now everything is understandable. So, IP case also we are putting IP per unit into IPB, right. So, bracket close. Now, similarly for secondary side, this minus ZSIS term, this is actually this minus ZSIS term. So, ZS is equal to also ZS per unit into ZSB, that secondary side base impedance, right, and this IS is equal to also IS per unit into ISB, the secondary side base current. This is equation 26, right. So, all this thing in can be put in the your per unit form, but all the time, but at the same time their base values all are multiplied, right. Now, dividing equation this 26 by divide equation by VSB. So, the left hand side this VSB term is there. So, all this equation you divide by VSB and using the base relationship of equation 17, 18, 19 and 20. So, whatever equations we have shown for base quantities, that is 17, this 17, 18, 19 and 20, you use that and substitute there. If you do so, you will get that Vs per unit, this part I think understandable, you can do it, right. So, Vs per unit is equal to Vp per unit minus Ip per unit into Zp per unit minus Is per unit into Zs per unit. In bracket we are writing all per unit to indicate that these are all per unit values of voltage and current and impedance, right. This is equation your 27. So, to replace all these things, whatever I showed, it is I put on the left hand side for your this thing. For example, IP is IPPU into IPB, ZS is equal to ZSPU and ZSB and so on. So, left hand side this has been worked out, right. So, this is actually your per unit impedance, I mean this is that your secondary voltage, primary voltage, all in a per unit, that is why bracket per unit is written, right. Next is, now we can write that IP upon IS is equal to IPB upon ISB. This also earlier we have told that primary ratio of primary to secondary current is equal to ratio of primary side base current by secondary side base current is equal to A. This we have discussed earlier. Therefore, IP upon IPB is equal to IS upon ISB. IP primary side IP upon IPB is IP per unit is equal to secondary side also IS per unit is equal to assume I per unit. That means, in per unit primary side and secondary side both the currents are same for transformer is equal to, we assume a single value, that is instead of P or S we will simply write that is I per unit, that is the per unit current, because per unit current primary and secondary side both are same. Now, using equation your 27 and 28, that means the previous equation. In this equation you put I instead of IP and IS, because IPPU is equal to ISPU is equal to IPU. So, this IPPU is equal to I and similarly ISPU is equal to I, both are in per unit, substitute. If you do, then you will get Vs per unit is equal to Vp per unit minus I per unit into Z per unit, right. This is equation 29, where Z per unit is equal to Z per unit secondary side plus Zs, that is Zp per unit primary side per unit values plus Zs per unit secondary values. This is equation 30, right. So, that means, this is the your what you call per unit all these equations secondary and primary side, this related to per unit, right. So, if you your what you call, if you draw now the simple circuit diagram, right, for the transformer. So, it will be like this. This is a per unit equivalent circuit of single phase transformer. This side is primary side, this is per unit voltage, secondary side per unit voltage, and this is the ZPU, right. So, that is that your ZSPU plus ZPPU, right. Now, Z per unit values can be determined from the equivalent impedance on primary or secondary side of a transformer. For example, on the primary side, right, when you primary side impedance in ZP, and when you go for bring that transformation no equivalent impedance. So, secondary side impedance was ZS, but it is referred to primary will make. So, it will be ZS upon S square, that you know, right. That means, your what you call, that means both side you divide by, because it is referred to primary, Z1 is referred to, the Z1 is the primary side your impedance you want to find out. So, Z1 you divided by primary side base impedance ZPB is equal to ZP upon ZPB plus ZS upon ZPB into S square, right. Now, this ZS this thing your what you call, this is ZPB into S square. Now, this is actually ZSB, because if you equation 19 and 20 we have made it, right. Just hold on, just hold on. Equation 19 and 20. So, this is equation 19 and ZPB is equal to VPB upon IPB, and this is equation 20, ZSB is equal to VSB upon ISB. So, you divide equation 19 by equation 20, right. So, that little bit exercise I have done on the right hand side here. So, therefore, if you do so, it will be ZPB upon ZSB is equal to VPB upon IPB into ISB upon VSB, right. That means, ZPB upon ZSB will become 1 upon S square, that means, ZSB will be S square ZPB. So, basically S square ZPB is actually ZS, right. That is going to the next slide. That means, Z1 per unit, this per unit value of impedance is equal to ZPU plus ZS upon ZSB, right. So, this is ZSPU also, because ZS upon ZSB. Therefore, Z1 PU is equal to ZPPU plus ZSPU is equal to, we are making it as a Z per unit, right. This is equation 31. Similarly, if you do on the secondary side, you will get the same thing, that Z2 PU is equal to ZSPU plus ZPPU is equal to ZPU. That means, that in per unit, that referred to primary side or referred to secondary side, that impedance, per unit value of impedance remains same. Therefore, per unit impedance of a transformer is the same whether computed from primary or secondary side. That means, this is the major advantage of transforming all the parameters in per unit values, right. So, after this we will take few good examples, right. We will take few good examples, and then we will come to the method of voltage control, right, different thing will come. So, first generally this your what you call this per unit transformation and this numerical, many things you have to understand. Whatever little bit theories we have seen, that is fine. Now all these theories we have to apply for this your what you call considering few numericals. This per unit system actually transformation not only for these small numericals, at the same time it is required for our power system analysis, right. For all sort of things, so whenever you study everything, that voltage, current, power, impedance, we consider everything is in per unit values. This makes our calculation simple, right, by choosing proper base values. First, next we will take one example, first example, we will take few example, such that things will be all different type of example, such that all the ideas will be clear, right. So, first one is a single phase 2 winding transformer is rated 25 kVA. That means, your 25 kVA means it is a distribution transformer, right, and 1100 by 440 volts, 50 hertz. The equivalent leakage impedance of the transformer refer to the low voltage side, that means if we take 1100 is primary, then 440 volt secondary. So, refer to the low voltage side is 0.06 angle 78 degree ohm. This is actually secondary side leakage impedance, right, refer to secondary side. So, using that means low voltage side, if we take 1100 volt as the primary side. Now, using transformer rating of as base values, that means this is 25 kVA base kVA, and this is your primary side will be 1100 and secondary side will be 440, right. Base value determine the per unit leakage impedance refer to low voltage winding and refer to high voltage winding, right. So, first let us assume high voltage side is primary and low voltage side is your secondary windings. That means, transformer rating is given 25 kVA, it is given, transformer 25 kVA is given. Therefore, this 25 kVA you make it divided by 1000, you make it 0.025 MV. Actually, when you solve numericals, rather than keeping base in kVA, VA or volt, my suggestion is everything you per base voltage case you transform it to you convert it to kilovolt, and whatever may be the base volt ampere, all the time you convert it to MVA. Then I think actually in my opinion, then things will be easier for you to calculate, right. Therefore, transformer rating is 25 kVA, here we have converted to 0.025 MVA, and primary side voltage is 1100 volt, that we have converted to 1.1 kV. Secondary side 440 volt, that is 0.44 kV, right. Next, MVA base, therefore, transformer its own rating you have to find out. Therefore, MVA base is equal to 0.05, VPB, the primary side base voltage you can write 1.1 kV and secondary side base voltage is 0.44 kV, right. Now, you have to find out base impedance on the 440 volt side of the transformer, right. Therefore, secondary side you are writing ZSB is equal to V square VSB square divided by MVA base. So, VSB equal to 0.44 kV square divided by 0.025 is equal to 7.744 ohm, right. Therefore, per unit leakage impedance referred to the low voltage side, that is ZS per unit. ZS EQ is given, this is given by ZSB, this ZS secondary side leakage impedance is given. So, it is 0.06 angle 780 degree ohm divided by base impedance on the secondary side, that is 7.744 is equal to 7.74 into 10 to the power minus 3 angle 78 degree per unit values, right. This angle is also given, right. This is on the per unit value of the secondary side, but you have to see that primary or secondary per unit values will remain same. Similarly, if ZP EQ referred to primary side, that is winding, that is high voltage side, that is 1.1 kV, that is 1100 volt, that ZP EQ will be A square ZS. We have seen just now for transformer equivalent circuit, per unit equivalent circuit or derivation, that ZP is equal to actually A square ZS. So, here I am writing ZP EQ is equal to A square into ZS EQ, right. So, that is actually N1 upon N2 whole square into ZS EQ, right. This way we are writing 1 is to A is equal to N2 upon N1, right. N1 upon N2 whole square, A square into ZS EQ into this one. So, ZP EQ is equal to 1.1 divided by your 0.44 whole square into 0.06 angle 780 degree. So, this ZP equivalent is equal to 0.375 angle 780 degree ohm, right. So, once your what you call this primary and this thing or what you call this ZPEQ, that means base impedance on the 1.1 kV side is that you can make it that your ZPB is equal to VPB square upon MVA base is equal to 1.1 whole square upon 0.05 is equal to 48.4 ohm, right. Therefore, ZP per unit is equal to ZPEQ upon ZPB is equal to 0.375 angle 78 degree by 48.4 is equal to 7.74 into 10 to the power minus 3 7 angle 78 degree, right. That means, this refer to secondary sides this value and refer to primary side also, you will get the same value, right. And this one, therefore, per unit leakage impedance remain unchanged, and this has been achieved by specifying V p base upon V s b rate, this thing is equal to V p, this is the rated value on the primary side 1.1 kV by V s rated, that is 1.1 upon 0.44 is equal to 2.5, right. So, that means, this small example we took just to show that whether you take refer to primary side or secondary side on per unit values, this your what you call the voltage impedance, per unit impedance will remain same. Thank you.